So this video will be dealing with the Unit 12 material from the review packet for the final exam. Okay, so again, please follow along in your packet. Feel free to stop, pause, restart as much as you need. Unit 12 dealt with states of matter, and that IMF stands for intermolecular forces. Okay, so starting off, if we're talking about states of matter, it asks you to draw a picture representing a solid, a liquid, a gas at the atomic level. So there are a number of ways you could have done this, but the basic idea, you just want to make sure that your solids, the particles are sort of the densest, and then liquids and gases each get a little bit more spread out. So something to this effect. I would say a solid, you want it to be all the particles fairly close together. They're kind of stuck in place. They don't really have freedom to move. A liquid would be a little bit more spread out. So these would look more like this. Still kind of ordered, but not nearly as disordered as the gas, which are gases. They're sort of all over the place, way more random, way more spread out. Okay? So they're sort of our solids, our liquids, and our gases. In 22, it asks what is the difference between an inter and an intramolecular force. So check out the difference in those prefixes there. An intermolecular force, you can look these up in definitions up in your notes, but these are the forces within one molecule. So the force holding together one thing. So examples of intramolecular forces would be ionic bonds, covalent bonds, metallic bonds, basically all sorts of actual bonds. Alright, your intermolecular forces, these are the ones that we were abbreviating IMFs, even though they both start with I. These are the ones that we were abbreviating that way earlier in the year. Okay, your intermolecular forces, there are three kinds, and those three kinds are London dispersion forces, which they're sometimes just called dispersion forces. Okay, make sure you know what they actually mean. We have dipole-dipole forces. And last but not least, you have hydrogen bonds. Now, even though we're calling it a hydrogen bond, it really is just an attractive force again. All of the intermolecular forces are between different molecules. They are not actual physical connections. So just to make sure we're clear on that principle, just make sure you know that intermolecular is always weaker than an intramolecular force. Alright, so an actual bond will always be weaker than an attractive force. Okay, so in the next question, number 23, for all of these, you were asked to identify the dominant inter and or intramolecular force in each of these. So the first thing you really needed to figure out was what type of solid do we have for each of these. Okay, so the types of solids we mentioned before were molecular, ionic, network covalent, which ones did I skip? Amorphous, and metallic. Okay, so your molecular substances, these are ones that we can draw Lewis structures for, and those show up in all things made up of all nonmetals. So we see a couple of those here. A is an example. Alright, because carbon and bromine are both nonmetals. PCl3 are both nonmetals, so this is also molecular. NaCl, however, is ionic. Sodium is a metal, chlorine is a nonmetal. So that's going to make our answer a little bit different. Magnesium is just a single element. That's a metal because it's to the left of the steric line, so we're going to say that's a metallic solid. And then HF, H is a nonmetal, so is F, so we're going back to another one that is molecular. Okay? So, knowing what type of solids they are allows us to now figure out what we can draw Lewis structures for. You can draw Lewis structures for any of the ones that are molecular. So that would be A, B, and E. Okay, if you don't remember how to draw Lewis structures, I suggest you go and look back at the Unit 11 video, because that went through sort of how to draw Lewis structures in detail. But anytime you have an IMF question, you really are figuring out what the Lewis structure should look like first. It's implied, essentially. Okay? So if you draw your Lewis structures for each of these, CBr4, whoops, wrong one. There we go. CBr4 is going to look like this. We'll have a carbon as our central atom, and then our bromines all connected. Alright. If you draw the Lewis structure for PCl3, it's going to look like this. Then if we move on to the other one we could draw the Lewis structure for, it would be HF, and that one would look like this. Now, the reason we drew the Lewis structure was because now we can decide what types of intermolecular forces, so intermolecular forces are showing up in molecular things, we have here. Now, the three are London dispersion forces, dipole-dipole forces, and hydrogen bonds. Dispersion forces show up in everything, so the first thing we can do, even if we're not sure if it's the dominant one, we'll go back and circle the dominant one later. So for now, let's just list them all. So we know that this one would have dispersion forces, because again, they're in everything. Previously, people were often abbreviating them as LDF. That's okay, I just want to make sure you actually know what they stand for. Dispersion forces are basically temporary dipole-dipole forces, more or less. Okay, so there we go. The next type were the dipole-dipole forces. Dipole-dipole forces only show up in things that are polar. So again, if you're having trouble with polarity, check out the Unit 11 video I made. But if we look at our polarity, because all the bromines attached to this carbon are the same, this molecule would be nonpolar. Okay. B, because of this lone pair of electrons right there, will be polar. And then HF, because these two atoms are different, they're not pulling on the electrons in the bond with the same strength, so this one would also be polar. Okay, so any of the ones that are polar will also have dipole-dipole forces. Okay, so that means this one will have dipole-dipole forces as well. And the last one will have dipole-dipole forces as well. Now I'm skipping over some of the other ones that aren't molecular, and I'll talk about why at the end. Okay, and then last but not least, we have to investigate for hydrogen bonds. Hydrogen bonds only show up when you have a hydrogen attached to a fluorine, an oxygen, or a nitrogen. So we don't even have hydrogen in A or B, so definitely don't have it there. But E does have hydrogen. We have to check for those FON elements, though. We see hydrogen attached to a fluorine, so this will qualify as hydrogen bonding. So I'm going to list that as well. Alright, so we have all of the IMFs listed, but it also asks you to circle it asks you to select the dominant one, right? So how would you choose the dominant intermolecular force? The dominant intermolecular force will be the one that is the strongest, or in other words, it is the one that's most important in holding this particular substance together. So, in order of strength, dispersion forces are the weakest, dipole-dipole forces are a little bit stronger, hydrogen bonds are the strongest of just the intermolecular forces. Okay, so that means in A, our dispersion forces would be dominant because they're the only thing that's there. In B, dipole-dipole forces will be dominant because they're permanent, whereas dispersion forces are temporary. And then in E, hydrogen bonds will be the most important because those are the strongest. Okay, so that's how you would sort of work your way through the ones where they are molecular. C and D are odd because they are not molecular, so we can't draw Lewis structures for them. This really goes into when we were talking about our solid states. We talked about the 5 different ones and sort of some properties and how to classify them. If something is ionic, it actually is held together with intramolecular forces, and those intramolecular forces would be ionic bonds. So the dominant intramolecular force in NaCl would be ionic bonding, which again is an intra rather than intermolecular force. Alright, and then for D is a metallic solid, so the dominant force here would be metallic bonding because it's a metal, which again would be an intramolecular molecular force. All right. So there are our there we go. There are the inter versus intramolecular force questions. Okay. So there is plenty more practice of this if you go back into this unit, but see what you come up with for these. Okay. Question 24, the next one is just some definitions. So again, you should look all these up in your notes, or you can Google them. Quick words here. Temperature is a measure of the average kinetic energy. So make sure you know the link between temperature and kinetic energy. They are the same thing essentially, or they're directly related. Diffusion and effusion are very similar. Diffusion is the idea that gases like to spread out. So the formal definition, they move from high to low concentrations. Effusion is basically a specialized version of diffusion. So effusion is when diffusion happens through a tiny hole in the container, like through the membrane of a balloon or something. And then vapor pressure is the pressure of a gas above a liquid. So think about as a liquid evaporates, you're increasing the vapor pressure because more and more gas will then be above the liquid. Okay? So our last question of Unit 12 was looking at a heating curve, and it asked you to label where the following phase changes would happen. Freezing, boiling, also known as evaporation or vaporization, condensation, melting, which is also known as fusion, and where you would be heating just a solid, heating up a liquid, and heating up a gas. Okay, there were many more specific questions we dealt with in this unit as well, so these are just sort of generic, making sure you know what goes where. But I suggest you look back at the questions from the old test from this unit, old homework questions, etc., because for some reason these always seem to trip people up a little bit. Okay, but the governing idea you need to keep in mind when we solve this problem is that anywhere we had what we were saying was a plateau, so anywhere there was a flat part, that's where a phase change was happening. Okay, and anywhere you had a diagonal, or a slant, whatever you want to call it, that's where you were heating one state of matter. So you're heating only one phase, in other words, no phase change. All right? So, knowing that, if we assess our chart then, we know that 2 and 4 are the two plateaus, so we'll make sure that those are the two phase changes. So at point 1, the question is what phase then do we have? At point 1, we're at the lowest temperature. So think about an example like water. At the lowest temperature, what is water? Well, if we have water and it's really cold outside, it'll freeze into a solid, right? So the first piece would be heating a solid. Okay, how do you know we're heating it? Because you can see that by the slant of our graph here, this means the temperature is going up and up and up and up, so we're heating up the solid. Now as soon as you get right here, as we move our way across, now we're into a plateau, so we do have a phase change there. The question is which phase change would that be? If you have a solid and you start heating it up, what happens to it? It melts, so that would be where melting, which again, it's also known as fusion, would occur. Okay, that would be the same temperature at which freezing would happen, but that would be if we were cooling it down rather than heating it up. Okay, if you move into line segment 3, let me actually put this off to the side here. So this would be a solid going to a liquid. So once we have gone from a solid to a liquid, that means we now have a liquid, right? So the next natural progression would be if we have a liquid, if the temperature starts increasing, that means we're heating a liquid. All right, and you'll keep heating that liquid until you hit 100 degrees Celsius for this particular substance. Once you get to 100 degrees Celsius, we now have another phase change happening, so it's got to be a liquid going to something else. If you heat up a liquid, what happens to it? It boils. So at 4, our phase change would be boiling, which this one has a couple names. We could say boiling. That's also known as evaporation. And you could even call it vaporization. They're all the same thing. But the key is that would be a liquid going to a gas. Okay? So if you convert that into a gas completely and then continue to raise the temperature, your last part of the phase diagram would just be to heat up your gas. So it won't change into anything else, but the particles will continue to move faster and spread out more and more and more. Okay? So again, these were just sort of generic, just what's happening where, but make sure you look back at some specific questions that go along with these as well, such as like, what is the boiling point? What is the freezing point? How long does it take for something to melt? Where would there be only a liquid present? Things like that. There are all sorts of different examples in the notes, so please make sure you take a look back at those as well. The last thing I want to note on this graph, just note that the temperatures that are marked over on the side are important. Okay, if you sort of trace over from this plateau, you see we're at 100 degrees Celsius, which is what we would call the boiling point. Okay, and if you trace over from our other phase change, you get to 0, which if we're heating this up, really we could call this the melting point, but we also call it the freezing point quite frequently, because remember, melting and freezing happen at the same temperature. It's just a matter of whether you're adding heat or absorbing it. Adding it or taking it away, releasing it. Okay? So again, make sure you look back at some of the specific questions from this unit. But those were all of the questions in the review packet from Unit 12. Our next video will deal with gas laws, which was all math and formulas.